A line of symmetry. It's just a line you can fold your graph over, and it's the same on both sides. If something is symmetric to the x-axis, or sorry, the y-axis, that's the first one I have here. That means if I took my graph and I folded it over the y-axis, it's the same on both sides. Okay, so maybe the graph looks something like this. Assuming I were a better artist, that really doesn't look all that symmetric, does it? Pretend that's the same on both sides. You guys know what I'm trying to do. So those are the same on both sides. If I fold it over the yellow line here, we get overlapping functions. In terms of the equation itself, you can tell because what happens is if you look at points on here, so this maybe let's call it the point 1, 1. This one is the point negative 1, 1. Whether x is positive or negative, the y value is the same. So the definition of being symmetric to the y says if x is positive, you get the exact same value as if x were negative. If something is symmetric to the x-axis, that means if I fold it over the x-axis, it overlaps itself. It's the same on both sides. So let's say I gave you something like this. Okay, if I fold over the yellow line, those overlap. If you look at your points, here's 2, 1, here's 2, negative 1. So whether the y is positive or negative, you're getting the same x value. Symmetric to the origin means they are exact opposites. So the origin actually requires you to flip over both the x and the y-axis to get there. So it might be something like this. Here's the point 1, 1. Here's the point negative 1, negative 1. Both x and y change signs when you're looking at the ordered pairs. So that's the 3 types of symmetry that we might see with our graphs. X-axis, y-axis, origin. If we're looking at a graph, then it's not too hard to tell. If we're looking at the equation, it takes a little more work. If I wanted to decide the symmetry, sorry, I'm still writing here. So if I want to decide the symmetry by looking at the equations, there are a couple different things we can do. If I want to check symmetry to the x-axis, okay, what we just said on the previous slide was if it's symmetric to the x, then whether y is positive or negative, we get the same thing. So what we're going to do is replace y with a negative y. What happens if you do the absolute value of a negative y? Okay, that's the exact same thing as the absolute value of positive y. Is that the same as my original equation? Yes. So whether y is positive or negative, I get the same thing. So this graph is symmetric to the x-axis. If you want to check y-axis, if it's symmetric to the y, positive and negative x give you the same thing. So if I plug in a negative on my x, does that negative disappear? No. So this is not what I started with. If I want to check origin, we do both of them. If it's symmetric to the origin, both x and y change signs. So I have a negative x equals absolute value of negative y. Now on the inside of my absolute value, I can drop that negative, but I still can't get rid of the negative out in front of my x, so this one is still not symmetric. It can have more than one type of symmetry, which is why I checked all three. It's also possible that none of them will work. This particular graph is only symmetric to the x-axis. Let's try another one. If I want to check the x-axis, what do I do? Replace y with a negative y. Is that the same thing as my original equation? No. Is there anything I can do to turn it into my original equation? No. So this is not symmetric to the x. I don't know what happened there. Okay, how do we check the y? We change our x to a negative x. All right, what happens if you take a negative to the third? Is it positive or negative? Negative 2 times negative x, be a positive. Is that what I started with? No. All right, how do we check origin? Both. The y is negative and the x is negative. Okay, just like we said above, a negative to the third is still negative. Negative 2 times negative x is positive 2x. Is there anything I can do to turn this back into my original equation? Yeah, if I divide by negative 1 on both sides, I get y equals x cubed minus 2x. That is what we started with. So this particular graph is symmetric to the origin. Let's try one more. Do you guys understand how we are getting these? So how do we check x-axis? What happens if you square a negative? Is that what we started with? Yes. So this one is symmetric to the x. How do we check the y? But if I square a negative, it's positive. Is that what we started with? Yes. How do we check origin? Since we're squaring those negatives, they both disappeared. And that is, again, what we started with. So this one is actually, yes, for all of them, symmetric to x-axis, y-axis, and origin. Do you guys understand how we're deciding this symmetry? If something is a function, so if it passes the vertical line test, sometimes we use the words even and odd instead of symmetry. This is also on that notes handout, so those were the last two slides, so you don't have to copy this definition down. Even is the same thing as symmetric to the y. Odd is symmetric to the origin. I always remember the O's go together. Odd is origin. How come I don't have symmetric to the x if I'm talking about a function? If it's symmetric to the x, it looks like this. Is that a function? No, if it's symmetric to the x, it fails the vertical line test, so it's not a function. So if I know it's a function, it can only be even or odd, symmetric to the y or symmetric to the origin. All right, so I'm going to put some graphs up here, and I just want to decide if they are even or odd or neither. What would this first one be? Even. This is symmetric to the y-axis. If I fold this thing over the y-axis, it's the same on both sides. Y-axis means even. What about this one? Odd. If I fold it over the y, it would look like this. And then if I folded it over the x, it's back to where it started. So 2 flips to get there. That's called an odd function. What would this one be? Odd. If I flip it over the y, looks like this. And then if I take that and flip it over the x, I'm back to where we started. What about this one? It has kind of the same shape as the odd. If I flip this over the y, it would look like that. If I flip this dotted graph over the x, what's going to happen? Yeah, it's going to be up here. So this one is neither. All right, if you know something is a function, symmetry is actually even faster to check. If it's written in function notation, first of all, we only have 2 options for symmetry, y-axis or origin. We could do the same thing we were doing before, or all we really have to do is plug in a negative for the x. So find f of negative x. When I do this, a negative squared is positive. So positive and negative x give me the same thing. That's symmetric to the y, when positive and negative x are equal. So the definition of even symmetric to the y, that means f of negative x is equal to f of positive x. So if you plug in negative x and get the original back, that is an even function. This one. If I put in a negative x, a negative cubed is still negative. It's not what I started with, so it's not odd. Or so it's not even. Odd says if you have the opposite x value. So if you think about odd was origin, and we said whether x was positive or negative, I go back to this, when symmetric to the origin, both the x and y change signs. So if you put in a negative for your x, you should get the exact opposite for your y. You should get the opposite of what we started with. Is this the exact opposite of what I started with? No, the exact opposite would be negative x plus 1. So this isn't what I started with, it's not the opposite, so this one is neither. This one, if I put in a negative. A negative cubed is still negative, minus negative is a plus. Is that what I started with? No. Is it the exact opposite? Yes. So if it's the exact opposite, that's odd. Do you guys have questions? Here is what I want to do. This first one, I just want you to think about what this means. If you have a point, 5, negative 3, okay, you can draw a picture if it helps you. Here's my point. If it is symmetric to the x-axis, what would that point be? That's the y-axis. If you flip it over the x, it would be 5, 3. So part A y, the point when you flip it over the x-axis changes the y value. So 5, 3. If I said I wanted to flip this thing over the y-axis, where would it go? -5, -3. C, if I flip it over the origin, that's over the y and over the x. Where does it end up? Remember, flipping over the origin changes both of their signs. So the 5 changes to a negative, the 3 changes to a positive. So let's do, I'm going to let you guys